All right, this is the last section in Unit 5. This is Unit 5, 12 notes, and we're talking about behavior, except now we're going to have implicit differentiation. And really nothing else changes except the implicit differentiations when you got two different variables in the same problem. So if you're doing a derivative with respect to x, remember you got to put a dy dx. We are having a Unit 5 test next week. So we are supposed to show that this thing right here, when you do the derivative, will give you that dy dx is this. So when I do the derivative of 4x squared with respect to x, that's 8x dx dx plus, I'm doing power rule for this, gives me 18y, and since I'm doing y, I must put dy dx. And then the derivative of a constant is 0. So anything that doesn't have dy dx, I'm going to get to the other side. So we have got 18y dy dx. And I subtract that 8x over. And then I divide both sides by 18y. And that gives me that dy dx is equal to, and then I reduce these by 2. So this will be negative 4x over 9y. So I have just shown that that's what the derivative is there. Note that dy dx equals 0 when x is 0, and that dy dx is undefined when y is 0. So this is kind of a big deal that you notice this. Dy dx is 0 when x is 0, and dy dx is undefined when y is 0. Those places correspond to the vertices for the major and minor axes and the ellipse. That's this ellipse up here. The four vertices are the critical points of the implicit relationship. The ellipse has horizontal lines at 0, 2. So 0, 2, there's a horizontal tangent line right there. And down here it's 0, negative 2. In other words, if I plug in 0, 2 into this equation, 0 and 2, I get 0 slope. And if I plug 0, negative 2 into this, plug 0 and negative 2, you can get a 0 slope. And then when y is 0 is when it's undefined. That would be a vertical tangent line. So like if I plug 0 in here, no matter what you get up here over 0, that is a vertical tangent line here and here. Okay, so in other words, where dy dx, when I'm looking for critical numbers, is where the top equals 0, and where dy dx is undefined is where the bottom equals 0. That's where this comes from. So that's those critical numbers we're talking about. In quadrant 1, on the intervals from 0 to 3, and 0 is less than x is less than 3, and y is 0 is less than y, and y is less than 2, dy dx is less than 0. Okay, so let's look at what that means. From 0 to 3, and from 0 to 2, it says dy dx is less than 0. Why? Well, that's the slope of this thing right here. This is decreasing, so that means your slope is less than 0 because it would be a negative slope. And then it says in quadrant 3, so down here, if you look going from here to here, we're decreasing again, so it's saying from negative 3 over here to 0, and from negative 2 up to 0, dy dx is less than 0 again because this slope is decreasing. And dy dx will be greater than 0 when x is from negative 3 to 0 and y is 0 to 2, increasing and then increasing again here. So that's what it says here. They just told you what I exactly just told you about. Dy dx is greater than 0 because the function is increasing here, and increasing here. Okay. Concavity of implicit differentiation. So now we're talking second derivative. So this says consider the following relationship using implicit differentiation to show dy dx again. So we're going to do the same thing we just did a minute ago, but we're going to do it with this problem. So 3 is I'm going to start from here and start doing derivatives. So 3 is my coefficient, so it stays like that. And then the derivative of x to the first is 1. And then minus the derivative of this, you take 1 times -1 is -1, and then it's y, so you're going to use dy dx, and again, you wouldn't have to put the -1 there. And then the derivative of 4 is 0. Leave your coefficient the same there, that 3. The 3 would be there, and then the derivative of cosine is negative sine. We're doing chain rule here, by the way. So it's negative sine, so I'm going to stick the negative in front of that 3. And we got sine y, and then we do the derivative of y, which would be dy dx again. So I need to get all my dy dx's on the same side, so I need to distribute this 3 over here. So when I distribute this 3, I got 3 minus 3 dy dx. And then over here, I got a -3 sine y dy dx. And now I'm going to get my dy dx's on the same side. So let's add this one over. Well, let's see, we're trying to get 1 minus. So let's add this one over to this side. So I'll get 3 equals 3 dy dx minus 3 sine y dy dx. And then let's divide everything by 3, because there's 3's in front of everything, and factor out the dy dx at the same time. So when I take 3 and dy dx out, I got a 1. Over here I'm going to have a sine y. So last I got to divide by 1 minus sine y. I'm going to divide that over here. That is my, because over here I got 1 minus sine y. These reduce out, and I'm left with dy dx equals what this says right here. Then it says no, dy dx not equal to 0, and that dy dx is undefined when y is 1. So in other words, what makes the numerator 0? When does 1 equal 0? That's never. That's why it says dy dx never equals 0, because the numerator is not 0. And then it wants to know, when is the denominator, when would the denominator be undefined or equal to 0? So if you got 1 minus sine y equals 0, that would make this undefined. So when 1 equals sine y, so what that means is we need to know, when is sine going to give you 1? Well, I hope we all know that from the old graph, if you start sine at 0, at pi over 2, you're at 1. At pi, you're 0. 3 pi over 2, -1. 2 pi, back up there, and this graph keeps going. So you are back up here at a max again at 2 pi from here, because the period of this is 2 pi. So that's why he says sine y equals 1 when y equals pi over 2 plus 2 pi n. And then it says for any integer n. In other words, this number can be any number like -6, 4, 3, no decimals, but that's ideal. That's when you're going to have undefined. In other words, at all these top points of the sine graph, that's when this function will be undefined. So that's where we're going to have vertical tangent lines wherever this is undefined, which is the same value. Then it says the derivative is positive for all values of, can't read that, only that's pi, therefore, maybe it says y, therefore the relation is always increasing. Okay, in other words, I got to read the paper because I can't see it. And I don't know when this is. There's my sheet. So let me back this up a second. Oh, I see. So they graph the graph over here for you. They graph this graph over here. So if you look at this graph is increasing the entire time. So that's what he's saying. This graph is increasing always. So this would be a monotonic graph. Okay? So we're going to go on down to that bottom part. Okay. All right, so this says for pi over 2 less than y less than 3 pi over 2, the second derivative is less than 0. So again, this is the same story. This is second derivative here. Oops, this is greater than 0. I'm looking at the wrong line on my sheet. So let me move this up. Maybe I think I got to go up a little bit. There we go. All right. So this thing says for negative pi over 2 to pi over 2. So negative pi over 2 for y, we're talking y values now. So we are talking about from right here up to right here. From here to here. It says the second derivative is greater than 0, which means concave up. So I hope you can see that's concave up in that little span right there. And then going on to the next part on the same graph, it says that this graph is concave down. That says second derivative less than 0 on this interval. So if you look at this graph right here, we got concave down from right here down here. And likewise, from right here up to here. Okay? So there's where the concave down is. It's wherever the second derivative is greater than 0 is concave up, less than 0 concave down, same as before. All right, so we're going to actually get into some examples. This is, again, this is just some problems that have x and y both in them. So we want to be able to find the values of this. So this says let f of x be a function such that dy dx is 3x minus 2y minus 8 if f of x contains the point 2, 1. So this means this point is on the original function. It's on the original function. Which of the following best describes the point 2, negative 1 on the graph? In other words, we want to know, is this going to be a max, a min? What will this thing be? So what we need to do is find out what sign we have here, okay? So we need to find the sign of this thing. So I'm going to plug in into dy dx. I'm going to plug in the point 2, negative 1. And when I plug that in there, I'm going to get 3 times 2 minus 2 times negative 1. All I'm doing is plugging my x, y's in, minus 8. And when I get this, I'm going to get 6 plus 2 is 8 minus 8. I get 0. So what that tells me is that 2 negative 1, because this is the derivative and it equals 0, 2 negative 1 is going to be a critical point. This is a critical point because it equals 0 here, this point 2 negative 1. So 2 negative 1 is a critical point. So what I need to do is find out, there's a couple of things I could do, but what I'm going to do is use the second derivative of this thing. So I'm going to do the derivative of this derivative, and then that's going to tell me by plugging in this point if I have concave up or concave down. So I want to do the second derivative of this function. So that means I'm going to do this derivative here. So the derivative of 3x is 3. The derivative of negative 2y is negative 2, but you've got y again, so you got to put dy dx in for that. And the derivative of negative 8 is 0. Now, we do not want dy dx here, so we're going to stick this whole thing right here back in for that dy dx. So this would equal 3 minus 2 times 3x minus 2y minus 8. And then I'm going to distribute that negative 2. So I got 3. And I'm going to simplify this mess. So I got 3 minus 6x plus 4y plus 16. And then I'd add these two like terms together and get 19 minus 6x plus 4y. Now that right there is the simplified second derivative of y. And now I want to know what kind of concavity this has at this point 2, negative 1. So I'm going to find the value of this second derivative at the point 2, negative 1 by plugging in 2 for my x, negative 1 for my y. Because I want to know, is this positive or negative? So when I get this, let's see, this is 19 minus 12 plus, this plus, and this would be minus 4. So this is going to equal 3, which is greater than 0. So this means concave up. Now remember, the what we had up here was that the 2, -1 was a critical point, and it's concave up at 2, -1. So if this is 2, -1 right here, we're concave up, so that makes this a relative min. That's a relative min. So that would be A, relative min there. Okay? Let's go down here to example 2. Example 2 says the points -1, -1, and 1, -5 are on the graph of a relation whose derivative equals this. Which of the following must be true? So what I want to do is plug those in to see what kind of points they are, because I'm not really sure. So I'm going to plug in the -1, -1 here. So I'm going to do dy dx, and I'm plugging in -1, -1 first. And when I plug that in, I get -1 squared plus -1, which is 0. So that's a critical point. And then likewise, I'm going to do the same with 1, -5. So I'm going to get dy dx when I plug in 1, -5. And that's going to be 1 squared plus -5, which equals -4. So what that tells me is the slope is negative right here. That's all that tells me. That is not a critical point unless I'm not seeing something right. Okay, so now I'm going to do the second derivative again, and I'm going to try to figure out what I get when I do the second derivative of this, plugging in -1, -1 to find out if it's concave up or concave down. So I'm going to do the second derivative of that. So the second derivative of y with respect to x is going to equal, so it's going to be 2x plus dy dx. And again, we don't want dy dx in here, so we're going to substitute this value back in for that. So it's going to be 2x plus x squared plus y. So now I want to get the concavity of this second derivative at -1, -1. So when I do that, I'm going to get 2 times -1 is -2. I'm plugging that one in there. -1 squared is 1 and -1, so this is -2. So we got concave down. So since this is a critical point, -1, -1 is a critical point because it's 0 and it's concave down at that point. So if that's the ordered pair -1, -1 that's concave down, that is a maximum right there. That is a max. Now, I don't really need to do any more with the -4 because it is not a critical point. So the main thing I'm worried about is finding max and mins over here. So I look at these, and let's see. So this is going to be that -1, -1 is a max. Now, if you want concavity at this point, if it was asking or telling you something about this point talking about concavity, then I could stick 1, -5 into this equation right here and figure out what kind of concavity there was there. But the slope at 1, -5 is -4. And then I could, in other words, right at that point, it's kind of going down like that, but it's not going to be a max or a min. So it's not really a super important point right there. Okay, let's go on to this next one. Oh no, this might be the last one. It is the last one. So it says concavity of an implicit relationship. It says consider the curve whose first derivative is defined by this thing. Determine the concavity of the curve at points for which you're going for y is 0 to pi. Give a reason for your answer. So what we're going to be doing here is we are again going to be looking for important points again. So what I want to do is I want to get the second derivative for concavity because I am trying to figure out concavity, which tells me second derivative. So I'm going to do the second derivative of this problem, which I would probably rewrite this as 3 over 3 plus cosine y to the -1 power. Now I could do quotient, Quotient will work, but I think it's easier when you got a constant to do a chain rule here instead. So I'm doing chain rule. So I'm going to get -1 times 3 is -3. Keep the inside exactly like it is. And then subtract 1 from the power. And then I'm going to go in and do the derivative of the inside, and I'm multiplying times this. Derivative 3 is 0. The derivative of cosine is negative sine y, and then you got to do the derivative of the angle, so this would be a dy dx here. So simplifying this thing, I got a -3 on top, and I got a negative sign, which makes a positive 3 sine y. And I'm going to move this thing down here to the bottom because it's a negative exponent. And then I got dy dx over here on the side. Now, if you'd have done quotient rule, you would have got this same thing right here. This would have been exactly what you had. But what I want to do now is I want to plug this thing. Again, you don't want dy dx in your second derivative, so we want to plug this thing back in for that. So I'm going to have 3 sine y over 3 plus cosine y squared. And then I'm going to have that times 3 over 3 plus cosine y. So when I simplify this, I'm going to have 9 sine y all over 3 plus cosine y to the third power. So this right here would be my simplified second derivative right there. Okay, so there's the simplified one. Now we want to know what's the curve going to be from when y is 0, when y is 0 to, can't remember what it said, pi, 0 to pi. We're only worried about the y values, okay? So first of all, I want to know, is there anywhere from 0 to pi that sine is 0? And notice there's only less than signs, right? We are not including 0 to pi. So I'm going to pull out my unit circle. And this is 0. Here's pi. So we are talking about not including, maybe I should have put an open circle here. I'm going to stick an open circle here because not including 0 and not including pi, we're talking about what are the y values from here to here. In other words, is there anywhere from there to there, anywhere from here to here, where this top part equals 0? And the answer is no. And if you think about this, it's the y values, and we're constantly above the x-axis. So we know this top part is positive the whole way. So that top part would be a positive. And then use the same reason, we want cosine of y. And, okay, that's a 3 right there because it's kind of hard to read. So you got 3 plus cosine y. Remember, cosine's the x values here. Well, there's some negative values here, right? But isn't the smallest value for cosine, doesn't cosine values always stay between -1 and 1 when you're going around the unit circle because the radius is 1 forever? So what that means is this value is always between -1 and 1. So when you take 3 plus this or 3 minus 1 would be the smallest in cubic, that's going to be a positive. So what that tells me is this thing is forever greater than 0. So this curve, the curve we're talking about right here, this curve is concave up from 0 less than y less than pi because of this right here, this whole thing right here. So that's your implicit differentiation, doing the same thing we've been doing. Little harder because you're dealing with dy dx in there, but I think you can do it. You just got to put some effort into it and keep going. Have a great day, and I will see you tomorrow.